Okay, off we go. Picking up where we left off last time, so we were talking about triple integrals, and just a quick reminder of what the big point is with triple integrals. Sometimes we're adding up stuff that accumulates over an interval. That's what single variable integrals are for. Sometimes this stuff accumulates over an area. That's what double integrals are for. And sometimes the stuff accumulates over a three-dimensional solid. Right? And that's what triple integrals are for. So the big challenge, I mean, most of what a triple integral is just it's just like a double integral, just more so, right? It's three-dimensional instead of two. It's so similar. The big challenge is that turning a triple integral into an iterated integral is now a problem of slicing up three-dimensional solids, which are harder to visualize, they're harder to draw, right? And so it's just, it's like really challenging, artistically and geometrically challenging double integral problems pretty much, right? So, okay, so I've got two more examples to show you and then we'll move on to the next thing. This is at first glance, an extremely hard problem. Suppose our domain is bounded by these 5 planes. Right, now I want to recognize if these were 5 random planes, just, cutting every which way, who knows what, this would be not feasible. Right? This would not be a fair question at all. So very importantly, these are not 5 random planes. These are 5 mostly pretty special and nice planes. Right? And there is a particularly convenient little trick that comes up surprisingly often in situations like this that makes it easy to get a foot in the door. And here it is. Again, really hard to see it coming unless you know to look for it. And in 2 minutes, you will know to look for it. And here's what you notice. 3 of these planes have no y's in their equations. Really important observation. So y'all will recall back in chapter 1, I think it was, we made the observation and we talked about the how to show it, etc. But the punchline is if there's no y's in the equation, it's parallel to the y-axis. So we have 3 planes here, and at a glance, we know they're parallel to the y-axis. Once you know they're parallel to the y-axis, I mean, you know that we're just going to be dragging kind of parallel to the y-axis, and so all I really need to do is kind of get my hands in any sense on these planes. And then I can just drag them parallel to the y-axis. So I'm going to look inside of the xz plane. I'm going to understand these equations inside of the xz plane, where they're just lines. And that's actually really easy. Z equals 0, Z equals X, and X plus Z equals 2. That's easy. That's high school algebra, right? And then recalling that, but these are planes, but as planes, they are parallel to the y-axis. We can just drag like this, and in fact, I see that we have a prism. Does everybody see how we get a prism out of this? Any questions about that? Feel free. All right, now we haven't touched the other 2 planes yet. There's more work to be done, but let's just take a moment to appreciate that we're 3 out of 5 done, and that wasn't that hard so far, right? So we just have to now look at the remaining planes, and we'll take them one at a time. This one's the easy one. Y equals 0. Well, of course, that's just this. And, how does y equals 0? There, okay, let's do it like this. There's y equals 0, and how does that cut through our prism? Well, makes a triangle, like so. The last one, yes, there's a little bit of effort in this last one. This last one, we have this equation. That's not parallel to any axis. Okay, but it's ultimately just one plane. It's not such a big deal. You can persuade yourself that it intersects the axes at 3 on all 3 axes. So it's going to be something kind of like this, and now you have to use your geometric imagination. We've got this prism heading this way, and we're going to cut it at this it's just angled in all three directions, right? And how does that cut through? And it's going to cut through and make some angled slice. If you were talking about cutting in a cooking context, they would call this cutting on the bias, I think. Is any chefs in the room correct me on that? Anyway, I think that's called cutting on the bias. And something like this. Now, how did I know that these points would be such that they make a line parallel to that? Well, I didn't. And so there's some other calculations that you have to think about. How do I know in particular where that point is? Well, that point is on that plane with that equation. It's on this plane with this equation. And it is on this plane with that equation. And so you've got three equations and three unknowns, and you can Math219 that, and you can find exactly where that point is. And once you know where that point is, you can do the exact same process and figure out where this point is. It's on three different planes. You have a little bit different algebra, Math218, etc. And you can just notice that these 2 points have the same y coordinate. It just works out that way. All right, is that cool? Is that satisfying? And y'all can fill in those details. Okay. Right, so there's our solid. How do we slice this up? Which of our 6 different orders of the differentials do we want to use to slice this up? It's really not obvious. At a quick glance, you just cannot tell. By the way, this is the fact that we can't tell yet makes this a good moment for me to bring up the following point. There are a lot of high school multivariable calculus classes out there that tell students, oh yeah, you can kind of look at the algebra that you're given, and whatever you take the thing that you see right there, and that's your bounds for your integral. And I say that's a bunch of nonsense. We can't even tell here. Even having drawn the picture already, I can't even tell which order the differentials should be in. Does that make sense? Right? So if you took a high school multi-class and if they told you this little story about how the bounds, and you can just lift them right out of the givens, in very narrow circumstances that those classes confine themselves to, that coincidentally happens to work, but it is not a reliable method. So make sure not to buy into that. That will get you into big trouble, for example, in a case like this one. Okay. All right. So how do we slice it? This is actually a fun exercise, and I think everybody should do this. Slice this in all 6 directions, all 6 orderings of your differentials. And what you will find is that you keep hitting corners. All of the 6 except for 1, you will hit a corner mid-process in your slicing. For example, if you say, okay, I'm going to do my dy slicing on the outside. Okay, well there's a y slice, and there's a y slice, and this is all good so far. I haven't hit any corners yet until, of course, moments later, you're going to hit that corner. After which, your slices are qualitatively different. Right? These dark blue slices touch this plane, whereas the purple slices don't. They touch that different plane. So that's a loser, right? You definitely don't want to do your dy on the outside. You're slicing through corners. You're going to have multiple iterated integrals. Nobody wants that. Right? Everybody see what I'm talking about? So try all of the different orders, and what you will find is that this one is the only one where you don't slice through a corner, mid-process. Okay. And then once you've got your differentials decided on, then of course it's the usual slicing procedure, and it's just a matter of playing the game. Now let me show you what I think is the better way to do this. The better way is to use my projection argument, which I think is very convenient in a great many circumstances. And notice that we have a good projection into the XZ plane, and just from the picture alone, all you need is the picture. You notice that this triangle, nothing more than a triangle, is the projection into the XZ plane. we like triangles. Triangles are pretty easy to slice up, right? So in the XZ plane, putting dx dz on the outside, that triangle shadow is going to give me my outside two bounds, like so. And by the way, you got to think through the details, but you have to do the dx dz in this order. If you switch them, you'll hit a corner in that shadow. Right, so you want to do it this way. Does that make sense to everybody, or is everybody following along? Okay, and then we're going to look at a particular point then in my footprint, in my shadow, and we're going to think about, okay, for those values of x and z, where does y start and where does y end? Well, y starts at that point, which is on this face, on which it's clear that y is 0. So our lower bound for y is 0. And then it ends at that point, which is on this face, which, wait a minute, okay, what was the equation of that face again? That face was, I already forgot. X plus y plus z is 3. And remember, easy to mess this up. Be careful to follow all the rules carefully. Y is what we're solving for, because we're looking for y bounds. And if you solve for y in that equation, that gives you that for your y upper bound. Yep.
Doesn't having the exterior-most integral be then z means that the slices are going to be horizontal?
Yeah, sure. Okay, now just to be clear, what you're suggesting is we're going to take these bounds for these differentials that we motivated from the point of view of a projection, and you're going to say, no, I want to reinterpret this as, let's look just at the z slices themselves. And absolutely, the z slices look kind of like that. Absolutely, and that works fine, because while there are corners up there where we would end it, and there are corners down here where we would have started it, there's no corners in the middle. So it works fine. Is that cool? Is that answer your question?
You work with both interpretations, they end up being the same.
Yes, in this case, yeah. And sometimes there are multiple orders of the differentials that are equally good, and if you take the slicing point of view versus the projection point of view, you might coincidentally end up on different equally good options, but both points of view will always give you reasonable options. Yeah. Okay. Yeah. Yep.
I thought we're not slicing it that way, like the gray area, because we're going to hit angle corners.
Say it one more time.
I thought earlier we said slicing it that way, like the gray area is bad because we're going to hit corners.
Yeah, that would be putting dy on the outside. If I were to say I want to put dy on the outside, right? There's the y-axis. Dy slices are like this, and yeah, that is bad, and you would hit this corner, and that would be a problem. But notice that's not what I'm doing. Okay. That's with dy on the outside.
You said what we're doing is different from slicing its projections?
Yeah, that's right. So the argument that I made here is a projection argument, not a slicing argument. Now, of course, look, the projection argument is just kind of a streamlining of the slicing argument. Right? It's really kind of the same thing, as you pointed out. Yeah, absolutely. But it just feels different. Anybody else? Oh, I'm sorry, yeah.
Without switching the bounds, because I guess the issue with the corners is just the fact that it's not continuous.
I missed the first part of it.
Instead of switching which differential you're using, could you make the function a piecewise function to deal with the corners? Oh yeah, absolutely. Yeah. And you're free to do that, except that that's going to double your work, right? And if also keep in mind, on an exam. I know I say this a lot, right? But it's not about answers, it's about reasoning. It's about, your demonstrated proficiency with the ideas. And if you double your work pointlessly,
it's not a good look, right? So you want to make an effort toward making the best possible choices. Is that satisfying?
Yeah.
Okay. Cool. Okay. All right. Let's see another example. This one is really artistically hard. It's just in a different way, but okay, so here we go. We've got, let me go into highlighter mode. We've got this surface, which y'all will recall from chapter 2, looks like so. And then we've got this surface, which y'all will recall from chapter 2, looks like so. And now we've got to figure out, okay, what is this region that's bounded in between these two paraboloids? And it's like I have kind of a bowl. I have a deep bowl and a shallow bowl, and I've got the shallow bowl kind of shoved inside of the deep bowl, and then there's going to be some space in between those bowls. Does that make sense? Does everybody kind of see what I'm trying to draw there? It's very hard to draw it well. The problem is, artistically anyway, when I say, okay, well, we're looking at what's in between here, that feels like what we're talking about, but it's not really right, because where the two lips of the two bowls kind of meet right there on this circle, there's some space that's trapped in between the bowls over here. But if I color that in, if I sort of do like this also, then it makes it look like I'm filling in what is actually the sort of the cavity that's defined by the outside bowl, right? So it's this weird thing where there's a pocket of nothingness in there, but there's orange region here, and then there's nothingness, and then there's an orange region on the back. I don't know how to draw that, right? It's just artistically challenging. So it's a tough one to draw, but there you go. Now let's think in terms of how we would slice this, and if you want to take a slicing point of view, you totally can. It's just really hard artistically. And here's my best effort on that. For example, if I were to take a Z slice, I think that Z slice, I'm going to need my glasses for this, be something like kind of like that. That's hard though, isn't it? I mean, geometrically, just trying to, what does this thing look like? And then as I slice it, what does that look like? By the way, it's really easy to accidentally misdraw your slice, and then you draw wrong conclusions from your forgivably but still wrong picture, right? And so it's a fraught approach. Really hard. I don't recommend it. I think this is a much better example to use the projection method. And hard though it is to draw the solid, I think it's pretty easy to see that the projection and the XZ point is just a disk. Does that make sense? Everybody kind of see? Yeah, it's just a disk, nothing to it. And, you can play games to see what the equation of that bounding circle is for that disk. No big deal. But we like disks. Disks are relatively easy. Okay, and then furthermore, for any point in that disk, we can talk about what happens as you go in the y direction. And, well, we're going to enter into our solid at a point like that is consistently on that surface. Every time. For every point in our disk, the lower bound for y will always be on that blue surface. And then, as we proceed along through our solid, we will exit the solid at a point like that, which is consistently on that surface, that equation. Everybody happy? Questions about that? So it's much easier to solve this problem from the point of view of projections. And let's see here if I can get this all onto the screen. Let's I'll do it like this. So looking at the projection into the xz plane, we put our dx and our dz on the outside. Either order you like, doesn't matter. X and z play sort of symmetric roles here. And slicing up that disk gives you these bounds. It's kind of a double integral slicing, section 5.2. Make sure you can do that, of course. And then again, this blue lower bound surface. This blue lower bound surface gives us that lower bound from that equation, and then this red upper bound surface gives us that upper bound from that equation. Everybody see the process there? Little details to be checked. And again, make sure to check through and make sure you're good with these bounds, these green outer bounds. Again, questions? Okay, cool. So we're going to move on to the next thing then, section 5.5. This is a massive, gigantic, enormous section. This, if it were me, I would have made this 3 separate sections. At least 2. But I think I'd probably like to do this in 3 sections because there's just so much material. It's going to take us at least a week. Best case scenario. Unlikely to actually work out as a best case scenario, but at least a week to do this, and probably 4 class meetings to get this done. So change of variables is a big subject. I like to segue into this by starting with single variable calculus. I've done this with various different things. We motivated the idea of derivatives by thinking, well, what's a single variable derivative? We motivated double integrals by thinking, well, what is a single variable integral? The chain rule, likewise, right? So I am a big believer in this. Start with single variable, figure out what it looks like there, make sure to take just the right point of view, and then the extension to the multivariable setting is, if you look at it just right, kind of the same thing. So that's what we're going to do here, and y'all have actually seen this before, I'm sure of it. The substitution rule, right? Everybody remembers the substitution rule? It turns out that this powerful, sophisticated idea called change of variables manifests in single variable calculus as the substitution rule, right? Our old friend. Right? So now I know you all know the substitution rule. I know you probably have a favorite point of view on the substitution rule. I'm going to take a slightly odd, very particular, probably not your favorite point of view on the substitution rule, again, so that once we take this very particular point of view, we can extend most conveniently to the multivariable case. So here it is, a little bit strange, but off we go. We're going to suppose that we have x given as some function of t. I'm going to call that function g. By the way, a lot of students are accustomed to doing substitutions with a particular letter of the alphabet. U, right? So commonly used U that people call it U substitution. There's absolutely nothing magic about the letter U, right? Substitution, you can do it with any letters you like, right? So I'm just going to call this the substitution rule. I'm going to use T and X. No particular reason. It can be any letters you like. Okay, so very often we think of this as just an algebraic relationship and kind of play algebraic games, and y'all will recognize the substitution rule. I've got it written down here already. Hopefully you all recognize this. Does that look familiar to everybody? As the substitution rule. In fact, sometimes students don't even think of the substitution rule as an equation. They think of it as a process, right? It's a here's how you do them kind of thing. But if you write that out as an equation, this is it. Also, very commonly, students know this in the similar looking form where it's stated with antiderivatives. Here I'm stating it as a statement about integrals. Make sure not to conflate antiderivatives and integrals. They are different kinds of things. Antiderivatives are functions. Integrals are not functions. Integrals are numbers computed with an expression called a Riemann sum. They're just not the same. Right? They're closely related. Fundamental thermocalculus shows how they're extremely closely related to each other. They are distinct as concepts. Okay, so this is the integral version of the substitution rule. So here's the take I want to give you on it. I want to think of this function g as literally taking values on the t-axis as inputs and then spitting out as outputs values on the x-axis. So t goes in and x goes out. I want to think of g as a function that goes from here to there. It's a function that goes left to right. Cool? Okay. All right. And then I hope it's not a big ask. If I can, yeah, there we go. If I were to take an interval, a specific interval, let's say from A to B, plug in all of those points, then I would get various points out. In particular, it would be this interval from G of A to G of B. And notice that tracks with the formula that we have here. This formula we have here, the substitution rule, the integral on the left is from A to B. The integral on the right is from G of A to G of B. So this domain creates as its image this domain, and the integral on the left is on that input domain. The integral on the right is on this output domain. Is that cool? Everybody's happy? Okay. All right. So 2 key points I want to point out as to what's going on here. First, I want to talk about this idea of a pullback. And probably haven't seen this before. That's okay. Before we recognize the pullback that's going on there, I'm just going to show you a trivial example. The trivial example, I'm going to say I have, let's say, g of t is x, and let's have this formula be t squared. Oh, let's make it weird. Let's make it t cubed minus t. All right, now it's just a function, no big deal, right? Is that cool, everybody? Oh, it's just a function, whatever. Okay. You give me a t, out comes an x. Let me say that differently. The function takes points from the t-axis to the x-axis. Points go left to right. Points go this way. That's why we draw the arrow that way, is because that's the direction points go. Input over here, output over there. Here's the weird thing. Expressions don't. They just don't. If I have an expression like e to the t, how would this function take this expression and rewrite it in terms of x? I would need to plug in for what t is. It means I would need to solve for t in terms of x. We don't know how to do that. Okay, so expressions do not go left to right. In fact, expressions go the other way. It's weird, but it's true, and it's once you see it, it's really kind of no big deal. If I have an expression in terms of x, can I rewrite that in terms of t? Yeah, plug it in. There's nothing to it. This x, right here, everywhere you see an x, just write t cubed minus t instead, and we get e to the t cubed minus t, just plugging in. And so this is what I like to call a pullback. It's a common term, actually. While points go left to right, expressions go from the right to the left. The act of plugging in, everywhere you see an x, you write a function of t. The act of plugging in takes expressions from the right to the left. And the kind of the motivation for the lingo is that points are pushed forward and expressions are pulled back. Does that kind of make sense? All right. So I know y'all have been plugging in forever, right? For years. This may be the first time that you've noticed, perhaps, that, yeah, there's a kind of a backwardness to the act of plugging in. Okay, so I claim that's all that's happening here when we write down the substitution rule, is this integral written in terms of x, that is an expression in terms of x. And the act of plugging in pulls it back and rewrites it as an expression in terms of t. All right? And in fact, you can see part of this, quite explicitly. I mean, in the process of plugging in, whoops, sorry, wrong color. In the process of plugging in, doing the pullback, I literally plug in right there, x, there's x, and I just straight up plug in g of t. Right, that's part of that pullback process. All right. Now, there is the question of what do we do about this dx thing? What are we going to do about dx? And I keep in mind dx represents a little piece of the x-axis. And in fact, let's think of dx as having been produced as the image of a little piece dt of the t-axis. Again, you take a bunch of points on the left, plug them into the function, you get a bunch of points on the right. So I want to think of dx as being the output after plugging in dt. Now, you can see from the picture, this interval from a to b is not the same as this interval from g of a to g of b. They're clearly different, right? It all depends on the nature of this g. G could be any function. It could be all kinds of weird, right? Who knows? And likewise, this dt is not the same size as this dx. Okay, so how are they different? And what I'm going to claim is that there is a factor. Dx is always some factor times dt. Something about the nature of this g function is going to tell us how much this little interval of size dt gets sort of stretched out to make this, as I've drawn it here anyway, larger output interval. And that factor, how much bigger it is what we're going to call the stretching factor. And conveniently, we already know what that stretching factor is. We already know what do you multiply by an input differential to get an output differential, right? That's one of the big things we talked about in chapter 2. That's what a derivative is. A derivative is what you multiply by input differentials to get output differentials. Right? So conveniently, our stretching factor here is easy to write down, and so we can rewrite then the dx as part of our pullback process. Dx, I can relate to dt by recognizing that I've got to plug in this stretching factor, which in this case is g prime. Okay, now, again, I know y'all know the substitution rule. This is almost certainly not a point of view that you've seen on the substitution rule. Totally aware. You might not even like this point of view on the substitution rule. Cool. No problem. This is a particular take, though, that's going to be really, really convenient in the next few seconds here as we try to generalize this to a two-dimensional setting. And so we're going to do these same two things. We're going to establish a pullback. We're going to recognize that there is an appropriate stretching factor. Other than that, we're just going to take an input domain. We're going to see what comes out as an output domain. And if that output domain is the domain for an integral, we pull it back to get a new integral on that original input domain. And roughly speaking, other than making sure that, that this is the image of that and, some plugging in the algebra, the main thing that we have to remember in the process of doing this is don't forget to insert your stretching factor. Okay, so here we go. Here's the two-dimensional equivalent. I'm going to start with a domain over here on the left. And I'm going to suppose that I have some function going like so. Now, what happens when I take all the points in this domain and one at a time I plug them all into this g function and out comes a bunch of other points and it's going to be some domain like this? I don't know. I've deliberately drawn it weird and ugly and undesirable because it might be, right? Even if you start with a nice pretty rectangle, this g could be a weird function, and so you might end up with something ugly over here. Cool, no problem. We can still talk about pullbacks. An integral defined on this domain pulls back to an integral defined on this domain. Most of the work is just plugging in, right? We've got this change of variables function that gives x and y as g of u and v. So that's all I plug that in. X and y are g of u and v. Formulas. Plug in. Nothing challenging to that. And the only little tricky bit is to remember that we've got to be careful with the stretching factor. We've got to be careful to recognize that how big a little piece of output area is. Not necessarily the same, in fact, presumably different from the little piece of input area that created it. There is a certain amount that this area is stretched out to make its image. And you just have to remember to insert that stretching factor into your pullback integral. This is just a rip-off of what we did here with, sort of interpreting the substitution rule. Same idea, 2 dimensions instead of 1. Okay. Okay, now, we're going to do an example just a minute. That said, let's take a moment to think about what that stretching factor is, and it's not so obvious in this case, right? In the two-dimensional case, I can't just say, oh, this is what derivatives do, right? We haven't talked about areas in relation to derivatives. So here's what the answer ends up being. I'll justify this later. I want to get some victories under our belt first, and then we'll talk about, getting into the weeds of why is this true. But that stretching factor is this formula. It's the absolute value of the determinant of the Jacobian, aka the derivative matrix. So absolute value of the determinant of the derivative matrix. Turns out that that's what the stretching factor is. And for the moment, trust me. And again, I'll give you a motivation for this in a bit. Well, Monday. Okay, now real quick reminder, don't forget that the derivative matrix is this right here. It's the matrix of all the appropriate partials assembled just so. Make sure that you assemble those partials correctly. It's very important. And then one other observation I'll make. The determinant of the derivative matrix, very often shorthanded like this, written as if it's a fraction. Why on earth would we do that? It's clearly not a fraction. Clearly, right? That's a determinant. Determinants aren't fractions. Why would I write it like a fraction if it's not a fraction? It turns out it behaves very much like a fraction. Right, so we've encountered this previously. We talked about situations kind of like this with the chain rule. Y'all remember with the chain rule? And I have mea culpa, right? I'm sorry to, I feel like I'm committing a math crime but you can pretend that things are fractions even when they aren't, and sometimes really good things happen, and sometimes you can, sometimes you can't. This is one of the situations where you can. We can treat this like a fraction in several critical moments because it behaves effectively like a fraction. Okay, one of those examples comes up very immediately. If I look at, let's see here. Yeah, okay, so let's think about this dA. This represents area in the xy plane. I'm going to call that dx dy. When we do integrals, usually we write the dA as dx dy. du dv, of course, we're looking at over here. And, of course, this is the stretching factor times du dv. Well, let's write that stretching factor, write that stretching factor as a fake fraction. Don't forget your absolute values. Partial xy, partial uv. Haven't really done anything yet. I'm just plugging in the formula for what the stretching factor is. And now here's why I say this behaves kind of like a fraction. The following is nonsense. The following is garbage. But it's very convenient garbage that will always lead you in the right direction. So this is very convenient, very valuable. It's as if those cancel. Now again, they don't. They don't cancel because this isn't a fraction. And the denominator down here, partial u comma v, that's not even a thing. I haven't even defined that. You can't cancel a thing if it's not a thing, right? So this is garbage, nonsense. Confess. But I mean, again, at the same time, it all kind of feels like we got u's and v's here. You got u's and it feels like they ought to cancel. And then, oh my gosh, check it out! It's like I have the x's. Let me get the colors right. The x's and y's, then give you x's and y's. It kind of, on some sloppy level, feels like it works. Everybody see what I'm talking about there? This sloppiness will always lead you in the right direction. And so, very convenient. And again, sloppy though it is, I'm for it. Okay, is that cool? Everybody happy? Okay, let's do one. We've got a lot going on, right? We've talked about pullbacks and stretching factors and change of variables functions, and it's a lot to keep track of. Before we do the example, let me give you an ultra quick summary of what our process is going to be. The summary is, if you are looking at an integral, if the domain for that integral, however ugly it may be, is the image of a domain that you like better, right? That's all you need for your domain to be the image of something you like better. The pullback process, right? The pullback process of just plugging in will produce an integral whose domain is your preferred, right, pullback domain in green there. All you've got to do is plug in exactly like you would expect, and colors. Don't forget to include your stretching factor. That's the takeaway. Your ugly domain that you're given, if it's the image of something else, pull back, plug in, don't forget your stretching factor. And again, this is just a rip-off of what we did with the substitution rule. Okay, all right, so with that in mind, here we go. Here's a real example. Here is an integral. The integral is on this domain here. I'm going to call this an undesirable domain. Let's take a quick moment to recognize what an undesirable domain this is. If I were going to slice up this domain, doing a regular iterated integral, dx, dy, dy, dx, whatever Well, as you're slicing it up, you're going to hit these corners, right? In whichever order you go, dx, dy, or dy, dx, you're going to hit both of those corners. That means this is going to be 3 iterated integrals, either way you go. That's triple the effort that, all else being equal, I'd really like to put into this problem, right? I don't want to have to do 3 integrals. I want to do 1 integral if possible, right? Does that make sense? Okay, pretty undesirable. Okay, so let's proceed along here. Let's continue reading. It says here that this domain is the image by way of this function. Cool. It's given as an image. That was one of the things we needed. I just need my domain to be an image. And furthermore, the statement of the question tells us it's the image of the unit square in the UV plane. So thankfully, and I did this on purpose for our first example, keep things as accessible as possible. We need to make this an image by some function of some domain. I'm giving you the function, and I'm giving you this pullback domain. Okay, so let's just think about the mechanics. How do we actually put this into effect? Most of our setup is done in the statement of the question, but notice I am going to have to compute this stretching factor. In order to be able to, actually compute this, I'm going to need to compute that determinant, absolute value of the determinant of the derivative. Okay, all right, so let's do that. Here's our function. X and y are functions of u and v. You take the appropriate partials. That's your derivative matrix. Don't forget to take the determinant. Don't forget to take the absolute value. Here's where things get a little non-obvious. How am I going to take the absolute value of this algebraic expression 4uv minus 9? It's not immediately clear. I can't just I can't say absolute value of 4uv plus the absolute value of 9. It doesn't work like that. Right, so we have a little bit of a problem here, a little bit of a bump in the road. Here's the good news. It's actually pretty straightforward because check it out. This u right there, I can tell you exactly what u is doing. I know I understand u completely from the picture. There it is. U on my pullback domain is always between 0 and 1. And likewise, v is always, again, there's v right there. V is always between 0 and 1. And so knowing that, 4uv is always between 0 and 4. And so 4uv minus 9 is always negative. What do you think? Everybody follow that argument? So how do I take the absolute value of something that's negative? Well, I hope you all remember this fact from I guess it would be high school, but the absolute value of a negative number is the negative of that negative number. Does that ring bells? Let me write it down just as an example. The absolute value of -3 is the negative of that -3 because it's 3. Right? Is everybody happy with that? Okay. All right. Okay, so this absolute value then is 9 minus 4uv. And it's kind of all over but the shouting, which is good because we're running out of time here. Let me wrap this up with plugging this all in. Our stretching factor, colors. Our stretching factor, we put right there, following the rule. What do I do with x? How do I plug back in for x? Let me remind you in our picture. Keep in mind, x is one of the outputs from our change of variables function. The change of variables function will explicitly tell you how to plug in for x. This change of variables function will come in the form of x equals some function of u and v, and y equals some function of u and v. And we've explicitly got that here. X is u squared plus 3v, and you notice I just put that right on in there. That's just plugging in, right? There's no tricky curve there. That's just stick it in there, right? Likewise for y, and lo and behold, keep in mind what we started with. We started with this terrible integral defined on this terrible domain that's full of corners. We have now rewritten it as a new integral on this new domain, everyone's favorite domain for a double integral, right? 0 to 1, 0 to 1. Can't get any better than that. 3 separate iterated integrals have now turned into a single iterated integral. And yeah, there's the polynomial inside here is a little bit uglier, but it's still a polynomial. This is still a pretty easy integral. It's just got several terms in it. This is a lot of work. So we turned a hard problem into an easy problem by doing a pullback with change of variables. And we're out of time. We'll pick up here. See a bunch more examples starting on Monday. Have a good weekend. Sure thing. See you later.
The reasoning is always